Hello, everyone. Thank you for being here today. Before we dive in, let me quickly introduce myself. My name is Divakar Duraiyan, and I'm a technical architect with over 15 years of experience in IT industry, including the last 10 years focused specifically on aviation technology. Over the past decade, I have had the opportunity to work closely on large-scale digital transformation projects within the aviation sector, particularly in areas like predictive maintenance, aircraft system integration, and data driven operational optimization. Through this work, I've seen how the industry is evolving, moving from traditional reactive maintenance models toward smarter predictive systems that leverage real time data and machine learning. One of the most powerful enablers of this shift is digital twin technology, and what we will be focusing today, how digital twins are driving the next revolution in aircraft observability. Modern aircraft generate more than 200,000 data points and up to 1.2 terabytes of operational data every single day. That's a huge data. That's a massive opportunity and also a challenge. Digital twin technology unlocks that data's potential by creating virtual replicas of aircraft systems. These twins monitor, simulate, and predict aircraft health with failure prediction accuracy of 97.3%. That's not a science fiction. That is happening now. And today, I will show you how this works, what benefits it brings, and how industries beyond aviations are adopting the same tool. Let's begin with what makes digital twins so powerful. First, complete visibility. Digital twins replicates the full aircraft environment, providing observability across every component, like mechanical, electrical, and environmental. Next one is predictive analysis. Twins can identify failure pattern 28 days in advance, which gives maintenance team a long runway to address issues before they escalate. System integration is key. Twins correlate data from thousands of sources into one unified operational picture. Finally, real-time monitoring. These systems continuously process telemetry data throughout the entire flight phase, not just during inspection. This combination of depth, integration, and immediacy is what sets digital twins apart from traditional monitoring system. The impact of unified observability is measurable, dramatic. Digital twins reduce the mean time to detect issues by nearly 90%. That is faster identification of problem. Mean time to resolve drops over 76%, meaning issues are not only detected sooner, but resolved faster. There is a 61.8% reduction in emergency maintenance, and perhaps most significantly, there is an 84.6% decrease in AOG events, which are extremely costly disruptions. This shift from fragmented monitoring systems to unified digital twin platform creates this kind of operational efficiency. So, how do digital twins get such deep insights? It starts with multimodal telemetry, vibration analysis, which uses high frequency sensors to detect tiny deviations down to 0.05 millimeter, often indicating early stage bearing wear. At a 20 kilohertz sampling rate, no subtle vibration goes unnoticed. Thermal imaging monitors temperature patterns, identifying electrical faults or fluid leaks. With zero point 0.1 degree Celsius resolution and full spectrum analysis, we catch problems that traditional sensors miss. Acoustic monitoring brings in sound. AI algorithms analyze frequencies beyond human hearing. With ultrasonic detection and pattern matching, anomalies are identified well before they become audible or dangerous. All this data, vibration, heat, sound, are fused by advanced algorithms to create one unified signal. Even when individual sensors look normal, these algorithms can detect combined patterns that indicates future failure. Let's look at three examples that prove power of digital twins. A major European carrier implemented digital twins across 137 aircraft. In 1 year, they saw a 93% drop in unexpected component failures. They prevented 18 flight cancellation by catching early signs of fuel bump detection, which is approximately saved over 4.3 million euro in AOG cost. And a North American cargo operator integrated engine and system monitoring. Despite legacy integration challenges, they reduced maintenance cost by 23% and extended component life by 14%. An Asian regional airline used a digital twins to detect APU failure pattern 21 days earlier than traditional systems. With AR guided repairs and predictive part management, they cut maintenance turnaround time by 42%. No matter the size or region, digital twins are delivering measurable return of investment and operational improvement. Digital twins observability relies not just sensor, but also intelligent architecture. Onboard edge computing allows raw data to be processed on the aircraft itself, even in mid flight. These distributed nodes can detect anomalies immediately. Data filtering algorithms reduce transmission by 87%. Only the most relevant data gets sent, saving bandwidth and avoiding overloads. Secure transmission system uses multi-channel communication for resiliency. For cloud integration, which enables fleet-wide data aggregation and analyze on the ground. This edge-to-cloud architecture enables continuous observability even in remote environments or during connectivity gaps. Digital twin data becomes even more powerful when made with visual through augmented reality. Failure probability mapping uses historical and real-time data to create component-specific risk maps. Technicians knows exactly where to look. Visual translations, which converts complex analytics into simple overlays. No need to interpret raw data. AR procedure guidance provides interactive repair manuals or instructions directly in the technician's field of view, which reduce error rates by 76.2%. These tools have cut maintenance by over 34% while improving consistency and quality. Technicians are no longer reacting, they are anticipating. As with any advanced technology, there are challenges. Data accuracy must exceed 98.7%. It requires constant calibration. A small sensor drift can lead to a false alert or missed problem. Legacy integration is complex. Most airlines uses over 14 plus different legacy systems, many built decades ago. APIs and middleware become essential to unify the ecosystem. Telemetry in flight is tough. Extreme temperatures and vibrations which demand redundant sensors and advanced error correction to maintain data fidelity. But by tackling these heads on, airlines achieve faster return of investment and greater long term reliability. Implementing digital twins is not an overnight process, but it can be faced strategically. Assessment phase, evaluating existing systems and data gaps. Prioritize systems with the highest failure impact. Data foundation, deploy the sensors, build storage, and standardize acquisition protocols. Ensure the data integrity from the start. Twin development, which creates model of critical system, train them with the historical data, and integrate AI and operational expansion. Scale to full aircraft and integrate with maintenance system. The total implementation takes 18 to 24 months, but many airlines see early return of investment within 7 to 9 months, long before the full rollout is complete. What's exciting is that aviation now influencing other industries. In power generation, turbines are monitored with the same techniques used in engines, which is delivering 93.6% prediction accuracy and cutting unplanned outages by 42%. In medical equipment, digital twins predicts scanner maintenance needs, which is reducing scan cancellation by 71.8%. In manufacturing, production lines uses predictive analytics to detect process trips, which is reducing defects by over 37%. The reliability and safety standards pioneered in aviation are now being applied to industries where uptime is critical and failure is costly. Let's wrap up with some key takeaways. Digital twins deliver transformational observability with 97.3% predictive accuracy. Integration is the linchpin. Success requires bridging a legacy system, but the return of investment is real. With an 84.6% reduction in AOG events, the investment pays for itself quickly. Looking ahead, technologies like quantum computing and next gen machine learning will push prediction accuracy to 99.8%. We also expect broader standardization, with organizations like Airing driving adoption across manufacturers and maintenance providers. This will make digital twins easier to implement, scale, and share across the industry. Thank you all for your time and attention. The future of aviation maintenance is intelligent, predictive, and interconnected. And digital twins are at the heart of the transformation. Thanks again.